Anyway, it's really my great honor and pleasure to introduce my best friend and Professor Gerald Fuller here, and to give us a lecture. I always tell Professor Fuller that for so many years I've been to his lectures before, and everywhere if you're able to get in, you're really lucky because the rooms are always packed. You got to be earlier. Okay, and he always have something new to teach you. I'm familiar with Professor Fuller. He was here last year and delivered a wonderful lecture now in the bio world, right? So I don't really want to spend too much time to tell how good a person he is and how compassionate he is. But in any case, I just want to read out the paragraph here is prepared. So I hope you don't mind, okay? So Professor Fuller received his PhD in chemical engineering from Caltech, and he's been a professor, and now he's what's called Fletcher joins two professors of chemical engineering at Stanford ever since he graduated from Caltech. And then, of course, his research interest is in the area of rheology and interfacial fluid mechanics. And his labs, he really has developed many, we should not use the word novel, right? We should use innovative, new techniques. And of course, we do have a rheometry up there in the lab in 7118, if you go there, and it's an optical rheometry, it's the best of its kind, honestly. And he has a textbook on the principles of optical rheometry, right? Anyway, and then he has many other, of course, a person of his position and with lots of honors and many, many awards. So I don't really want to labor myself. And then I actually had a copy of his full CV. Probably, I've never seen a CV that thick. Okay, you can actually have a PhD thesis, which I don't want to read out. So I just want to briefly mention a few prestigious awards that Professor Fuller has received, including the Bingham Medal from the Society of Rheology and Cox Medal for excellence in fostering undergraduate research. And I think it should also include high school students, right? And then he was named one of the 100 engineers of the modern era by the American Institute of Chemical Engineers. He's a member of the U.S. National Academy of Engineering and AICHE and a fellow of the American Physical Society. Without me laboring out with all this long list of awards and prestigious things you have received and so on, and can we have the honor of Professor Fuller? I give you the floor to you.
Thank you. Well, whenever I have an opportunity to come to this beautiful part of the world, I grab it. And I've been here all week enjoying Hong Kong. And it's really wonderful for you to include me also back in UST, because this is where I count many of my really most wonderful academic friends in this department. Of course, Professor Gao, I first met her when she was a PhD student herself in Cambridge. And over the years, it's been wonderful to associate with you, and now here at UST. And I saw up here that this is the Hong Kong Jockey Club Institute that we're, and I'm actually going to the Jockey Club tonight. Stanford has the Stanford Alumni Association of Hong Kong has its barbecue tonight. So we're going there to welcome the Hong Kong high school students who were admitted into Stanford. So it'd be fun to see this jockey club from a couple of different vantage points. I even see a cardinal up here in the front.
Right.
But no, that's not the Stanford cardinal, is it? It certainly is. Well,
I'm a member of the Alumni Association, and they didn't tell me, so I've got to find out.
oh, okay. Well, it's 6:30 at the jockey club. So, but it's really. Oh,
Which one?
well, this is the one on the way up to Stanley. You know,
Happy Valley.
yeah, right, I believe it's there. Stanley, wonderful little town. I was able to go there on my bicycle just a couple days ago. So I'm going to tell you a story today about contact lenses, but it's really a story that has to do with a number of issues concerning the interfaces in our body. We're really nothing more than a collection of really complex interacting interfaces. A little closer,
Yeah.
okay. And I'm concerned about one of these interfaces this afternoon, and that's the tear film of your eyes. And this is a marvelous structure that protects our ocular environment, keeps it moist, keeps it free of contamination. And many of us wear contact lenses on our eyes, and this presents some additional processes that we need to be aware of. So I'm going to tell you today about drainage, dewetting, and contamination of contact lenses. It's the work of graduate student Saad Bamla, and we have an undergraduate intern working with us this summer, Chu Chai. And this is a picture that somehow you got a hold of for this advertisement. So you have here an eye, and we have on top of it perhaps a contact lens. And this very thin layer of liquid, the tear film, needs to be extremely stable. And how does the body maintain that stability? So here is an eyelid, the upper eyelid. And this person, I think, was up too late the night before. It's not my eyes. I've had worse eyes. But you notice these small glands. Okay? These are called meibomian glands. We have them on our upper eyelid and our lower eyelid. Now, the tear film is mostly water, but it has some important proteins in it. One of them is lysozyme, which is a bactericide. So what lysozyme will do is it'll kill bacteria that happens to land in the tear film. There's also mucins that help with wettability. These are aqueous and soluble. On top of the tear film is an insoluble layer. It's called the meibomian lipid layer. These are produced here on these glands. So when we blink, we spread this insoluble layer of lipids on top of the tear film. And this has a very, very important role, not only in controlling evaporation, but also through its mechanical properties, controls mechanical stability. Now, if it doesn't work very well, this happens. This is an image with a fluorescent dye added to someone's eye that's suffering from dry eye disease. And as we age, this is unfortunately a more prevalent hazard that we face. This tear film has become unstable, and it's dewet, and it's very painful. If you wear contact lenses, this can be even more of a problem. It can happen even more frequently. So we're trying to understand why this tear film is stable, why it becomes unstable. You can collect this lipid material This is a former student. She's now graduated. She works at Genentech now. And she's collecting meibomian material from her father. So this is her dad. Okay? So you have to be careful if you visit my laboratory. You might be asked to make a contribution. Okay?
Is that legal?
Perfectly legal. He was actually for his contributions. It was a co-author on one of our early papers. Now these are insoluble. That is, they don't dissolve in water, but they love the interface. And a tool that you use in interface science to study these type of materials is called the Langmuir trough. Now, some people call it the Langmuir-Pockels trough because it was really invented by a woman, Agnes Pockels, but made very popular by Irving Langmuir, who got the Nobel Prize for his work in interfacial science, using this very simple idea. If you have an insoluble layer, you first fill this up with water up to these barriers. And then you spread this insoluble layer on the water. These molecules can't dissolve, and so they're stuck on the surface. They have nowhere to go. If I now compress, bring these barriers in, you compress them. This device simply measures the surface tension. That's all. It's called a Wilhelm balance. And you measure the surface tension with the film. Without the film, it's 72 dynes per centimeter, as we know water is. And what happens when you spread this on there, this decreases, so you get a positive difference. It's called the surface pressure. It's a thermodynamic quantity, and it's used to characterize the thermodynamic behavior of these lipids. And you get extremely complex and rich thermodynamic behavior. This is the area per molecule. This is the surface pressure that you measure with this Langmuir trough. So as you compress it, the surface pressure increases, and you bring these lipids together. Many of them will undergo a phase transition. This is a first order phase transition. This is a simple cartoon showing a first order phase transition from what's called a liquid expanded to a liquid condensed. Some people think of this as a gas phase and this is a liquid phase. This is really like the two-dimensional version of a PVT diagram. When you now convert this to your full phase diagram. And these, and in many cases, you get tremendous long-range order. So phospholipids are an example, or a fatty acid is an example. When you put these at the surface, you get long-range order. And as you compress it by increasing the surface pressure at various temperatures, you'll go through different phases. This long-range order has been recognized, and I'll show you how you measure this. And the nomenclature that is used to name these phases is adopted from the liquid crystalline literature because they resemble some of the phases that you get in these three-dimensional systems. You see similar organizations in two dimensions. So this would be similar to what you would see in a layered structure like a smectic liquid crystal. So at room temperature, for example, you might go from a hexagonal close-packed structure. But what's interesting is that the head groups may be on the lattice, but the tails now are free to adopt orientations relative to that lattice. So that you might go from a nearest neighbor orientation to a next nearest orientation. If you squeeze on it high enough, you may eliminate the tilt in the tail altogether. So this is the reason why you get this very rich phase diagram. Now, we're going to talk about 2 insoluble lipids this afternoon. Later, I'll add a third one, cholesterol. We're going to talk about mylum. This is this very complicated mixture. It's not just a single molecule, but it's a mixture of fatty acids, waxy esters, and cholesterol esters. It's a complicated mixture. Remarkably, this, even though it's such a melange of different molecules, it self-organizes. You'll see this in the X-ray data. DPPC is a phospholipid that is present in our lungs. You'll find a cousin of it in our eyes. We choose to study DPPC because it's saturated and is more stable in the laboratory environment. So we use this as a model lipid, and you'll see the behavior, how these 2 materials control drainage and dewetting on a contact lens. It's really quite remarkable. So this is the thermodynamics of these systems. These are room temperature isotherms, where we have the area per molecule. So we're squeezing on the Langmuir trough and measuring the surface pressure. Here's mylum. It's rather structureless. DPPC, though, has this first-order phase transition from liquid expanded to liquid condensed. You can see the domain structure by adding a fluorescent tag to the system. What happens is that at the low pressure phase, the liquid expanded, that's where this fluorescent tag will exist. If you squeeze on it and you start to develop liquid condensed phase, that will expel the tag molecule. So you can use epifluorescence to nicely visualize the domain structure. Now, this I'll talk about towards the end when I talk about contamination. These lines you see here, that's a texture of a contact lens. Okay. So you're seeing here, and I'll talk about this later, this 2-phase structure having been deposited directly onto a contact lens. Otherwise, here it's on the surface of water. So we have these 2 lipids, the real material from our eyes, and then we have this model system. Now you get the structure by looking at X-ray diffraction. You do low grazing incidence X-ray diffraction. So you bring X-rays onto the surface at a very low angle, and if you have an ordered material, you'll get diffraction patterns that you can measure. Those diffraction patterns, you can interpret them and determine the lattice structure. Is it cubic? Is it hexagonal? And then you can also tell the tilt angle of the aliphatic tails that are coming up, and also the tilt direction. So you get a lot of information from this experiment. So this is what you get from DPPC. You get this diffraction peak here, and you can analyze it and using some standard molecular models, and you can construct the phase diagram. But now you can identify different phase geometries for DPPC. If you now turn to mylum, you actually get much more complex structure. Even though this is a mixture of different molecules, you get a much more complex ordered structure. In fact, it's a superposition of a strong phase and a weak phase. We've determined that it self-organizes into a cubic lattice. Here are the geometries that we're measuring, the molecular, the dimensions of the unit cell, and the tilt angle. So it's really quite remarkable that this material that we spread, even though it's such a mixture, self-organizes so well. Now, if you look at the diffraction pattern as a function of temperature, what you'll see is that these strong peaks that we measure at room temperature ultimately melt. The eye is actually colder than physiological because it's exposed to air. So there is still structure even at the temperature of the eye, which is about 34 degrees centigrade. Now, this is a healthy person, what they produce. Very well organized material. What about a person that's suffering from meibomian gland dysfunction or dry eye? What you see in that case is a lack of organization. They are unfortunately not producing this highly organized material. And we believe that the consequences of this is that the mechanical properties of what they produce do not allow their lipid layer to properly stabilize the material. Which brings us to the next part. We talked about the thermodynamics, we talked about the structure. What about the mechanical properties? So Professor Gal mentioned rheology. So I'm a rheologist. I'm interested in how complicated soft materials respond to deformation and flow. Most rheologists study bulk materials. But what about the interface? Okay, we have here an aqueous layer, but it's coated with phospholipids. And we've seen that these are highly organized. There's a possibility that they can also have a very interesting rheology. Not just a surface tension or a surface pressure, but they can respond to deformation by supporting stress. And so there's a relationship between stress and strain or strain rate that means that in two dimensions there's a rheology, there's a viscosity, there's a interfacial modulus. We'd like to measure that. Well, here's what we came up with years ago, and it's now commercially available. This is an interfacial stress rheometer. It's a very simple idea. Remember when we were children, we learned how to float a pin at the surface of water? Well, that's really all we're doing. Our pin is a very slender magnetic rod. And we move that rod with these coils that moves back and forth between two channels, so we shear the interface. We know the force, so we know the stress. Stress in two dimensions is force per length. We measure the position of the needle, so we know the strain. The relationship between stress and strain is a modulus. We move the needle back and forth at a certain frequency. And this allows us to measure not one modulus, but two. Is the material more viscous? That's the viscous modulus. Or is it more elastic? That's the elastic modulus. So we measure the interfacial, elastic, and viscous moduli of the interfaces this way. And this is done in a Langmuir trough, so we can control the thermodynamics. So here's what you get. Here's DPPC. Remember, it is an organized monophospholipid. It's in our lungs. Here, the open symbols are the viscous modulus of DPPC as a function of surface pressure. This is the elastic modulus. So it's really more viscous than it is elastic. What about meibom? Remember, meibom is this very highly organized material. Oops. Orders of magnitude more viscoelastic. And we think that this is the key to why it's so successful in stabilizing material film. So as we increase the surface pressure, the surface moduli go up orders of magnitude. Ultimately, it's more elastic than it is viscous. And this controls the fluid mechanics of the tear film. There are two processes that you can think of immediately. One is drainage. We have a liquid film that's subjected to forces. It can it can flow over the surface of the eye. It can drain. So here is the aqueous layer. Here's this insoluble meibum. Perhaps this is a contact lens. And it's subject to evaporation and also drainage. So what are the consequences of interfacial rheology on this drainage problem? And if it drains, becomes too thin, you can get spontaneous dewetting. So it'll actually break. And there's a famous result that is if the thickness E is less than a critical value, this is the surface tension, the density, and the gravitational acceleration. The square root of this ratio is called the capillary length. This is the contact angle that this liquid makes on the surface of either the eye or on the surface of a lens. You can calculate this, and if the thickness of this film becomes smaller than the capillary, it'll spontaneously break. Now, our system, of course, is more complex than this because it's not just surface tension. It has a rheology associated. This is a simple way to start to think about this problem of dewetting. If the liquid becomes too thin, it'll spontaneously dewet. But if that surface has an interfacial viscoelasticity, that's going to stabilize that film. It doesn't want to stretch anymore. So the interfacial rheology we expect to help stabilize this against dewetting. We'll see if this is actually the case. So here's a little bit of fluid mechanics. Here's your eye. Here may be a contact lens on it. This is an aqueous layer. Here's an insoluble layer on top of it. We're going to allow it to drain. So we'll first look at drainage. When it drains, we can analyze this very thin film with a very simple fluid mechanical analysis called lubrication theory. So this is a pressure-driven flow, so it'll be parabolic. But the surface, we don't know the surface velocity. Ordinarily, what we would do to solve this as undergraduates is we would use a boundary condition, the no-stress boundary condition. But that's not the case here. We have an interfacial viscoelasticity, so this can support the stress. We don't know what the surface velocity is. Now, here are the dimensionless groups. It's a very thin liquid layer, so we can use lubrication analysis. The bond number for the geometry of our eye means that gravity dominates surface tension effects. But there's something interesting here that's new in this problem, and that is something called the Boussinesq number. This is the dimensionless ratio of the surface viscosity to the bulk viscosity, or the surface stress to the bulk stress. If this is 0, then there's no interfacial rheology, and we would use the familiar zero stress condition. What if it's extremely viscous, to the point that it becomes inextensible? Then the Boussinesq number would be infinite. So this number can go from 0 all the way up to an infinite number. So you have the fluid mechanics equation for lubrication. You have a boundary condition, no slip at the lower boundary. Here's the tangential stress condition. And you can write that down. And here's your Boussinesq number. This is the ratio of the interfacial stress to the bulk stress. If this is 0, then the gradient, of course, as we're familiar with, is just 0 at the top. So you can solve this. What we're really interested in, what we can measure is H, the thickness of the layer as a function of time. Okay. As it drains, H is going to drop. So we want to solve this equation. It's complicated because of this boundary condition, but we can solve it analytically in two limits. We can solve it analytically in the limit of 0 Boussinesq number and infinite Boussinesq number, and you get this very simple dynamic equation for the height at at the top of your eye. It's just a square 1 over the square root of time, where this is a dimensionless time. It depends on the radius of your eye, the initial thickness of the layer that's draining. And alpha is either 1/3 if it's 0 Boussinet's number, or 1/12 if it's infinite. So alpha goes between these two limits. In between, we can't solve this analytically, but it's easy to solve numerically. And you get these results. So this is what we want to measure. We want to measure the height as it drains. This lower one, that's 0 Boussinet's number. And then if it's an infinite Boussinet's number, of course, drains more slowly. So how can we measure this? Here's our Langmuir trough. So we can control the surface pressure. We can spread the layer. It could be mivum, it could be DPPC. Bring it up to some surface pressure. Here we have a dome. On the dome, we can put a contact lens. This will come up, and it'll capture a thin film of liquid. Above it is an interferometer, and it measures the thickness of this layer at the apex as a function of time, continuously. So it's a very simple idea. This is for drainage. How do we monitor dewetting? Well, we have an imaging system that is very successful at imaging any diffraction patterns that appear once dewetting starts to occur. So here's what the experiment looks like. From the side, you'll see the dome come up. We measure now the thickness at the apex using an interferometer. Here is the imaging system that looks at dewetting. Pretty soon you'll start to see dewetting happen right here. You can see the diffraction patterns. We can analyze those diffraction patterns and get the thickness of the film during dewetting. So it's a very simple experiment. Here is drainage, here is dewetting. When we raise the dome up, we get a strain. That is the area that we elevate through the surface, divided by the total area is a strain, an area strain of about 16%. This is a rather modest dilatation of the surface. So we published the drainage results in Soft Matter recently. You can read that. And here's again how the experiment works. We first spread some material at the surface. We then increase the surface pressure, elevate the dome through the surface, and measure and use interferometry to measure the thickness as a function of time. And this is what we measure. Here's the film height, the thickness of the film as a function of time. And this is pure water. And the fitting parameter alpha is 1/3, just like it should be for pure water, no film. If we put DPPC on the water at a surface pressure of 15 millinewtons per meter, you can see that it slows down, and alpha, we fit it to the same equation, and it's lower. It goes from 0.3 to about 1/5. Mivum is extremely effective because it's very viscoelastic. And you can see it really slows down the drainage. And that's part of the stabilization success of this material. Now let's look at dewetting. So here's the imaging. We're going to start the experiment, and what we'll do is we'll enhance the image and we'll measure the wet area divided by the total area. So the wet area, this ratio will initially be 1 during drainage because it has not dewet. Once it dewets, this ratio will start to diminish. So let's watch an experiment. This is on a particular type of soft contact lens, and this is no film, just pure water. It's just draining, and now you can see it starts to dewet. You see this ratio diminishing over time. So this is the Dewetting experiment. So let's look at the influence of having these layers on top of this film. So we'll have pure water, DPPC at 10 millinewtons per meter, mybum at the same surface pressure. Remember, mybum we expect to be more successful than DPPC because it has a higher viscoelasticity at the surface. Here's the experiment. Water dewets almost immediately. Here's DPPC does a better job, but the winner is mybum. So this material that we have, every time we blink, it really does a wonderful job of slowing down drainage and postponing dewetting. Now, there are other processes that can influence drainage and dewetting. And we wanted to, we've talked about interfacial rheology, and that makes sense, that if we have a more viscoelastic layer on top, it should help. There's another phenomenon that surfactants can produce, and that's called a Marangoni stress. In fluid mechanics, we need to have a boundary condition. Now, normally, if it's just surface tension, then it's quite simple. If you have a gradient in surface tension, that will drive flow. So for example, if surface tension at this point is higher than at this point, you'll get a flow in this direction. It's called a Marangoni flow. You see it all the time. When you put a drop of soap on the surface of water, you see it spread immediately. That's because the soap reduces the surface tension at that point. The high surface tension of the water around it pulls it. Okay? It's a very strong effect. Well, this can happen also in our eye. So we might be able to see this if we look at how fast we elevate the contact lens through the surface. We do it very slowly. Perhaps we won't disturb this distribution very much. If we do it fast, perhaps we will. That may produce a surface flow, and that will either stabilize the film or destabilize it. It all depends on the direction of that interfacial Marangoni flow. So let's look at that. Well, for the two insoluble layers, mybum and DPPC, if we do this experiment and we change the elevation speed, how quickly we bring the contact lens through the surface, you see that over an order of magnitude, all the data lie on the same curve. So there's no Marangoni stress that we've measured for insoluble layers. But there are other kinds of surfactants that manufacturers use to help stabilize tear films. These are often soluble surfactants. So what about soluble surfactants? Now, the other thing that happens is that when you bring the dome up, the height of liquid that you capture also increases with the speed. And that's simply because you have a greater hydrodynamic pressure, so you're able to trap a thicker layer of water. So that's not surprising. Mybum traps a thicker layer than DPPC. So mybum is successful for a number of reasons. It slows down drainage, postpones dewetting, but it also holds a thicker layer. But what about soluble surfactants? How do they behave? Well, a very popular one that's often used is called SDS, sodium dodecyl sulfate. This is a soluble surfactant. The interesting thing about SDS is it has no surface rheology. So that's not, if it does any stabilization, it's not because of interfacial rheology. It may be because of Marangoni stresses. Let's see if this happens. Well, it has a huge effect. Now, with a soluble surfactant, concentration is is calibrated according to something called the critical micelle concentration. So if you have a very low concentration of surfactant, these surfactants are soluble, but they are unorganized and individual. Above a critical micelle concentration, you start to form micelles, and they behave as a reservoir of surfactant. You see that this has a very big effect. Here are drainage data as a function of time. The thickness is a function of time. Above the CMC. Above the CMC, you've got a lot of surfactant. And the time scale to absorb molecules onto the surface is very short. It's a hundredth of a second. Look at this time scale here. It does stabilize, adding SDS does stabilize it, but above the CMC, it's on the order of a few seconds. But you can see a very strong dependence on the elevation speed that we did not see with an insoluble layer. We're seeing it, a very strong effect with a soluble layer. So we believe that this is evidence of Marangoni stresses. If we now go below the CMC, what happens? Now you don't have as many solvent surfactant molecules. It takes more time for them to reach the surface. The time scale for absorption is 3 orders of magnitude slower. So that if you do have a Marangoni stress, it's much harder to eliminate it. The Marangoni stress is there because you have a distribution of surfactants at the surface. You have a very slow absorption process, so that concentration profile can remain for a longer period of time. And you notice here that the drainage times have been extended dramatically. So that's one effect. You also see, again, a strong effect on velocity. The reason that you have this strong effect is because of the capture height. If you do have a Marangoni stress, that means that you've got a spatial distribution of surfactant at the surface. We don't seem to have that for an insoluble layer like Marangoni. It doesn't exist. We saw that. For the soluble systems, if we capture a very thin layer, it's much more difficult to replenish that surfactant at the surface. And so that at slow velocities where you're capturing a very thin layer, we expect to have a slower drainage, and that's what we saw. As you go to higher elevation velocities, capture a thicker film, then it's easier to replenish, and you get a faster drainage. So with these soluble systems, very different than the insolubles. One, depends on whether or not you're above the CMC, the critical micelle concentration, or below it. And it depends on the velocity of how quickly you present the contact lens to the inferior. Now we're going to go to the last topic, and that is contamination. Now, I don't wear contact lenses, but if I did, I would be told on the package to clean them, okay, or throw them out, okay. And you may not follow the instructions. Well, when you're putting a foreign object in your eye, and you have a lot of complicated molecules that can adsorb onto that hydrogel surface, what is the consequence of having that adsorption? Will it also change dewetting? Well, we're going to study again MIBO. DPPC is our model system, but cholesterol is another interesting molecule in our tear film. So it's interesting to also look at this material. Now we want to adsorb this. Now we're going to adsorb it onto the lens and then look at dewetting. How do we absorb it? Well, again, we're going to use a linear trough. Here's the barrier. We're going to spread the material. It could be cholesterol, it could be DPPC or mybum. Here's our contact lens. We'll bring it up and we'll capture a sessile, a little droplet. On that drop is this insoluble layer. And then we'll, with a syringe, we'll diminish the thickness of this sessile drop until we deposit the layer on top of the lens. So that's how we accomplish it. So we will capture a drop on top of the lens. We'll diminish the thickness of the drop until we deposit the layer onto the lens. Then we can look at dewetting, but we'll do some image analysis. We have an instrument called a 2-photon microscope that allows us to look at the structure of these lipids deposited on the surface. So at the air-water interface, we use epifluorescence. So we add a fluorescent tag to our insoluble layer. Here's DPPC at this surface pressure. Here's cholesterol at this surface pressure. Here's mybum. You can see this highly organized two-phase system. We're at the surface pressure, we have a coexistence between the liquid condensed, that's the dark, and the liquid expanded, that's the light regions here. Here's cholesterol. Mybum is a very, very unstructured but very viscoelastic material. So this is at the air-water interface. Now we're going to deposit on the surface of the lens. Here's what you see on a lens that's made by Bosch and Long. You can see what we like about this lens is it has a texture, so you can see it. Here's the liquid condensed phase, surrounded by liquid expanded. And now we have the 2-photon microscope that allows us to capture the intensity of the fluorescent signal as we penetrate into the lens. And you can see that here we have two surface pressures at 6 and 9 millinewtons per meter. And you can see that this material is sequestered near the top surface. Now, this deposition, when it occurs, happens at when we deposit it. It's a dewetting process, basically. And you can see the structure of the DPPC. Here's the moving contact line during the deposition process. You can see as we sweep away, we leave remaining behind this deposited DPPC. Here's the 2-photon microscope. This is, as we penetrate in, you can see that after about 15 microns or so, we're into the lens and you don't see any more fluorescence. So it's trapped at the surface. Cholesterol is different. The penetration, it penetrates into the lens and to about 60 microns or so. If you now look at this as a function of time, not distance, so we're looking just at the top of the lens, and now we're going to turn on a movie, and you can watch it diffuse into the lens. So here's time evolving. We're staying at the surface, and you can see it diffusing away into the lens. So unlike mybum, which stays at the surface, cholesterol goes down. Mybum stays, like DPPC, stays at the top. So this is what you can deposit on your lens if you don't clean them. What happens? Okay. So now we're going to look at dewetting. So here's the story. Here's the wet area over the total area. Here's time. Here's an uncoated lens. Hydrogels are wonderful because they're very wettable. They don't de-wet very easily. DPPC, it actually improves it. So that's not a problem. We don't have DPPC in our eye. What do we have? We've got mybum. Look what happens when we deposit mybum on a contact lens. We get strong de-wetting. at these two surface pressures, the low surface pressure and at the 20, you get even more dewetting. Cholesterol, remember, it sinks down into the lens, and so not surprisingly, there's very little effect of cholesterol contamination. Why does DPPC actually improve it? You would expect that if you deposit DPPC on the surface, it should make the surface more hydrophobic because the tails are sticking up. But what people have measured, we haven't done this, but what people have measured on glass and also Pyrex is that if you put down DPPC, it reorganizes into a bilayer. And here you can see the hydrophilic head groups pointing upward. And we think that this is why we're seeing enhanced stability when we have DPPC on our contact lens. Mybum, unfortunately, cannot reorganize this way, and we get a very strong dewetting with that contamination. So what have we learned? Insoluble surfactants, because they have an interfacial rheology, enhance stability. They enhance it because they slow down drainage and they postpone dewetting. Soluble surfactants, which can be are also introduced in formulations to help with dry eye disease. They also can stabilize the film, but they do it through a different effect, not through interfacial rheology, but through Marangoni stress. And finally, if you have contamination by mybum, which of course is inner eyes, that's going to make the surface of your contact lens more hydrophobic and enhance dewetting. So read the instructions and clean your contact lens. Just throw them out. So thank you so much for giving me your time this afternoon. It's always wonderful to be here. Thank you.
Thank you so much. We really I learned a lot from you. I don't wear contact lenses, but I'm thinking of other related issues. But anyway, so let's have the honor of having Professor Fuller answering some of your,
Questions? Do you have some? Yeah.
Thanks for very informative talk.
Okay.
It's very long. I think it's very very complicated, the whole story. So I would just like to raise two questions.
Yeah.
So the first one is you mentioned a lot about how this lipid layer contributes to the viscoelasticity and it helps with the prevention of evaporation. But also in the tear film, we also have like a mucin and all these kind of protein and then the gel-like thing. So they also have this contribution to the viscoelasticity of the tear film. And also in the market, there are a lot of these artificial tears using, say, the pseudoplastic polymer solutions act as the artificial tear. So which it actually, I think it more mimics the mucin layer instead of the lipid layer. So can you discuss a little bit about the contribution of these two things?
So mucins are soluble, as opposed to mybum, which is insoluble. But you're absolutely right. The tear film is a complex aqueous mixture, and there have been artificial tear film solutions recipes that have been devised, and we've looked at these. We collaborate with a company called Cooper Vision, who makes contact lenses, and we've studied this, and it's quite different. The artificial tear solution, at least the recipe that we use from them, has protein in it. Protein will go to the interface, denature, and cause you get a two-dimensional gelation. So you get a rheological stabilization for that reason. If you put mybum on top of that, you'll get enhanced stability. So mybum is really important. But you mentioned evaporation. Now, there's controversy about whether or not mybum really reduces evaporative loss. And you'll find papers on both sides of that story. The processes that I've described here happen in the order of maybe a minute to 3 minutes. Not long enough to get significant evaporation. So I don't think that that's playing a significant role, at least in our experiments. Yes.
So in your mathematical description of the events, one of your terms was very dependent upon gravity.
Drainage.
Right. And we have a group, I'm not sure if there's anyone here from it, I was looking to see, in aerospace engineering where they make remote sensing contact lenses. And the thing that the professor talks about is for ocular pressure measurements for glaucoma medication.
Yeah.
But he's in an aerospace engineering department. So I have a feeling he deals with increased and decreased gravity. So what does increased or decreased gravity do to this whole process?
Sure. So I analyzed a very simple drainage problem where it's gravity driven, of course, and that's going to be turned off in the absence of gravity. Of course, the ocular pressure associated with glaucoma is very different. That's an internal pressure. But it's really that simple.
So you're going to have a very different dewetting situation in zero gravity and a very different dewetting situation in...
Well, the dewetting event may be identical, but the process leading up to the diminution of thickness to that critical thickness that induces dewetting is going to be very different in space than it would be here on Earth. Of course, we're blinking all the time, and that complicates everything. It helps.
It's hard to blink when you're in a high
Can you do an experiment inside the accelerating elevator?
There you go.
Sorry. Right.
Oh, yes.
Oh, it's very interesting talking about the film viscosity, surface viscosity. When we talk about this kind of surfactant on the water, usually we think about one layer, just like one layer of all the material packed together.
Yeah, like a monolayer.
Yeah, one monolayer. And when you measure that viscosity, so you measure how the angle of tilting, that will be something like.
It's still a monolayer because it's a long molecule.
That's right. So this is somehow, how can that related to the viscosity?
Yeah, it's...
In a sense, we usually understand.
Yeah, so it's remarkable that a monolayer can produce such a large effect. And we're talking about an interfacial rheology. So it has different dimensions because stress is force per length instead of force per area. But a simple monolayer of something like a fatty acid, okay, an insoluble fatty acid, very simple molecule. It's 22 carbons on its tail. That can, if you go to a high enough surface pressure, it flows like a liquid crystal at the interface, completely different. Mygoma is more complex because it's not strictly a monolayer. It's a multi-layer, probably 3 or 4 molecular dimensions thick. But it really is true that these monolayers, and I give a talk just on interfacial rheology where I give examples of spreading a monolayer of a polymer amphiphile. Completely different fluid mechanics. Completely different. So really quite remarkable.
We need more than 1 hour to understand better.
I have the time.
Actually,
Be careful, I'm a professor.
from chemistry.
Here you see enhanced wetting because from bilayer, right?
Mm-hmm.
Mentioned.
Yeah.
Classical.
That's a hypothesis. We haven't proven that.
So yeah, well that's quite reasonable. But how about the classical? Classical is like hydrophobic, right? Hydrophobic, like classical. Classical, yeah. See, classical also enhances wetting.
Which
Glass.
In the when you have three, you have Melbourne, you have EPC, and then you also look at cholesterol.
Yeah, cholesterol it's an amphiphile. Well, people think of it as a non-polar molecule, but really it's an amphiphile. So it's different than well, it has both a positive.
PPC, right?
It's very different.
Yeah, for PPC it's easy to form this bilayer.
Right.
But the cholesterol, I don't know what's the mechanism. I mean,
But remember that cholesterol actually went into the lens, so you may not have significantly altered the surface of the lens in that case. But it really is an amphiphile, and it does have a head and a tail.
also for the monolayer, normally do you really consider it's a two dimension? Because for two dimension, actually there's no really first order transition, right? That's
Right, and so, well, no, you really can't, thermodynamically, you can get a first order phase transition. This has been well documented for these monolayers. But when it comes to the mechanical properties, nothing is two-dimensional. And that's why we deal with this thing called the Boussinesq number, the ratio of surface stress to bulk stress. Talk about the mechanics, nothing is strictly two-dimensional. It's really a 3D problem. You go to very high Boussinesq number, then you start to restrict most of the stress to the interface. So we like to operate in that regime for that reason.
For use a fluorescence microscope to monitor this film, is it better to use a booster angle microscope?
We've used booster angle microscope. The fluorescence can be, certainly for the lens contamination where we can penetrate into the lens. Then it's really a conoscopic.
Because in that case you don't have to label it.
Well, booster angle microscopy has the advantage of not requiring labeling, but it's hard to get the resolution with a booster angle, the lateral resolution and the vertical resolution you can with fluorescence microscopy. But we have used booster angle microscopy in many cases. It's hard to do it on the surface of a lens, though, because you're relying on the booster condition, and that may or may not exist on the surface of
Wow.
If you ask question, who wears contacts?
Yeah, we should ask questions.
Well, that's what I find out,
Many people wear glasses.
It's safer, and when I give this talk, I find people blinking a lot more.
We want to generate
That's
more
right,
feelings.
that's right. It brings a tear to your eye.
Happy generate tears. Are they different from when they're angry or upset?
Yeah.
Sad tear films and happy tear films, are they different? Do they have different chemical compositions that MPC or MEMS?
Well, I see another PhD face.
Well, thank you so
welcome.
much. It's really a wonderful lecture.
My pleasure.
And really